Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase, one continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once: time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and the motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 12, we cover the crucial reality anchoring filter of sensor model independence. This is the mechanism that ensures we are discovering laws of nature, not merely documenting the idiosyncrasies of our tools. The skill you will gain is the disciplined skepticism to ask of any claimed discovery: does this pattern belong to phi, or does it belong to the thermometer, the radio telescope, or the particle accelerator? Our core question is, how do we know the rule belongs to reality, not to a particular instrument? This question cuts to the very possibility of objective science. We never perceive phi directly. We perceive it through a cascade of interactions. Phi influences some probe, light, an electron beam, a mechanical arm. The probe interacts with a sensor. The sensor produces a raw signal, a voltage, a pixel count, a click, and we then run a reconstruction pipeline to infer a phi sentence. At every step, the instrument imposes its own signature, its own accent. A rule that emerges from this process could be a fact about phi, or it could be a fact about the glass in our lens, the gain in our amplifier, or a software bug in our reconstruction code. The firewall must have a strict protocol to separate the two. The core concept is a law must survive sensor model diversity. This means we must validate a candidate rule across at least three distinct measurement modalities and verify the integrity of the entire measurement chain through forward model inversion. We do not trust a rule witnessed by only one kind of eye. Let me state the audio equation that defines this protocol. We say the requirement is simulate, measure, reconstruct, recover the same rule within uncertainty. We can write this as a cycle. S of M of phi, D R of D, G of R of D, approximately G of phi. I will explain each symbol. Simulate, S. We start with a hypothesized phi pattern that obeys the candidate rule, G. We use our best understanding of physics to simulate what raw data a perfect instrument of a given type would produce from this phi pattern. This is the forward model, M. In the real world, phi, the actual phenomenon, interacts with the real instrument. This instrument, with all its imperfections, produces a raw dataset D. Reconstruct. We apply our reconstruction pipeline R to the raw data D to produce an estimated phi sentence. Recover the same rule, GRD approximately G phi. We then check if the estimated phi sentence satisfies the original rule G. The approximately equal sign means within the combined uncertainties of the simulation, measurement, and reconstruction. If this cycle holds, if we can predict what the instrument should see from a phi pattern obeying G, then measure, then reconstruct, and find G still holds, it is strong evidence that G is not an artifact of that instrument. But this is just for one instrument type. The firewall demands we perform this cycle for multiple fundamentally different sensor modalities. Now, why is this necessary? The failure mode it prevents is pareidolia, the human tendency to see meaningful patterns in the noise and glitches of a single complex apparatus. This is the origin of countless false discoveries: N-rays, polywater, cold fusion, various anomalous signals in particle physics and astronomy that later vanished when the detector was recalibrated or replaced. By demanding sensor model diversity, the firewall forces us to triangulate on reality. If three different ears hear the same melody, it is likely a real sound, not a tinnitus in one ear. To understand this, consider an analogy from a context where truth is vital and instruments are fallible. The diagnosis of an illness in a remote Afghan village with limited medical resources. A villager has a fever and cough. One instrument, a simple mercury thermometer, shows a temperature of 39 degrees Celsius. A proposed rule or diagnosis G1 might be malaria. But a wise doctor knows the thermometer can be misread, or the fever could have many causes. He invokes sensor model independence. Modality 1, thermometer. He takes the temperature again, confirming the reading. Modality 2, stethoscope. He listens to the lungs. Does he hear the crackles characteristic of pneumonia, a different rule G2, or is it clear? Modality 3, blood smear microscope. He takes a blood sample. Does he see the plasmodium parasites, evidence for rule G1? The diagnosis malaria, rule G1, only earns a high confidence license if it survives across these independent modalities. If the thermometer says fever, but the lungs sound clear and the blood smear is negative, then the malaria rule is likely false. The fever might be from a different cause, or the thermometer might have been faulty. The symptom, fever, was real, but the inferred rule, malaria, was an artifact of relying on a single sensor, the thermometer reading, without cross-checking its meaning against other physical traces of the disease. The firewall of good medicine is this multi-instrument validation. It ensures the diagnosis belongs to the patient's body, not to the quirks of one tool. In Holophase, the patient is phi. The symptoms are the raw data D from various instruments. The diagnosis is the candidate rule G. Sensor model independence is the multimodal check. Now, what is the formal meaning in Holophase terms? Different sensors interact with different derivatives or aspects of phi. An optical telescope is sensitive to certain spatial and temporal derivatives of the electromagnetic component of phi. A gravitational wave detector is sensitive to strain derivatives of spacetime itself, a different aspect of phi. A particle collider's calorimeter is sensitive to yet other derivatives related to quantum fields. Critically, different sensors mix omega, k, and v differently. An optical sensor might have excellent spatial resolution, good K, but poor time resolution for very fast events, poor omega. A microphone array has good temporal resolution for sound frequencies, omega, but poorer spatial resolution, K, unless the array is very large. The forward model M for each sensor must describe this unique mixing. A true canonical constraint, which concerns the invariant relationships between omega, k, and v in phi, must preserve these invariant relations despite the different mixing imposed by each sensor. The rule G recovered from the reconstructed phi sentences should be the same, within uncertainty, whether it came from data mixed by an optical, acoustic, or thermal sensor. Let's connect this to energy as tele. Energy is a derived quantity from omega pay v-side relations. Therefore, energy tallies must agree across instruments within their uncertainty bounds. If you measure the energy of a phenomenon using a calibrated microphone, an infrared camera, and a strain gauge, and they all report consistent values, after accounting for the different aspects of phi they probe, That is powerful evidence that the energy tally is a real feature of the phi pattern, not an artifact. Disagreement signals artifact, not mystery energy. If one instrument reports a huge energy burst and others see nothing, the firewall conclusion is not that a new form of energy was discovered, but that the first instrument had a glitch, was miscalibrated, or was measuring something else, like electrical interference. The energy tally must be sensor invariant to be canonical. Think of it like assessing the wealth of a family in an Afghan village. One sensor modality is to count livestock: sheep, goats, cows. A second is to assess land holdings, jeribs of irrigated and dry land. A third is to evaluate the quality of the house: size, construction, furnishings. A robust assessment of the family's wealth tally should correlate across these three independent modalities. If a family is said to be rich because they have a large house, sensor 1, but they have no livestock, sensor 2, and little land, sensor 3, the wealth signal from the house is likely an artifact. Perhaps the house is inherited and dilapidated, or it's used communally. The true wealth tally must be consistent across modalities. Disagreement tells you to audit your sensors. Was the livestock count done at the wrong time of year? Or your model. Does wealth in this context mean liquid assets, not fixed property? The operational interpretation of this firewall function is the gold standard of interdisciplinary experimental physics and the core of multi-messenger astronomy. When LIGO detected gravitational waves from a neutron star merger, that was one sensor modality. The rule, a model of binary in spiral and merger, predicted certain omega pay Vivae relations in the GW signal. But for the rule to be fully licensed, it needed confirmation from other independent modalities. Crucially, Fermi and integral telescopes detected the gamma ray burst seconds later, and optical telescopes found the kilonova, all from the same patch of sky. Each of these, GW, GRB, optical transient, involves utterly different sensor technologies: laser interferometry, gamma ray scintillators, CCD cameras, and probes different derivatives of phi, space-time strain, nuclear EM processes, thermal emission. The fact that the same underlying event, a phi pattern obeying the rules of general relativity and nuclear astrophysics, consistently reconstructed across these modalities within the expected time, direction, and energy windows provided breathtaking validation. It was the ultimate exercise in sensor model independence. A signal seen in only one of these channels would have remained a candidate event. Seen in three, it became a licensed discovery that transformed astrophysics. The firewall role is to block the epistemic failure of single-channel dogma. It prevents a scientific community from becoming so specialized and invested in one type of instrument that they mistake its outputs for the voice of God. It mandates collaboration and cross-checking across technological paradigms. Let's state clearly what assumptions are allowed and forbidden. You may use a single instrument to discover a promising anomaly or propose a candidate rule G. You may develop sophisticated forward and reconstruction models for that instrument. You may not license a rule as a law of nature based on evidence from only one sensor modality or one instrument design. You may not dismiss contradictory results from other modalities without a rigorous joint audit of all forward and reconstruction models. You may not attribute sensor-specific features, like a resonance frequency of the apparatus, to a new property of phi. What happens when the check fails? When a rule cannot achieve sensor model independence, when it appears robustly in one modality but vanishes or contradicts findings in others, the firewall imposes a license consequence. The rule remains a candidate rule, its license perpetually provisional, until independence is achieved. If independence is actively disproven, other modalities rule it out, it is archived as sensor-bound, a documented artifact of a particular tool, useful for teaching about instrumental effects, but not a law of phi. Now, we must state the explicit prediction and falsification for instrument independence. Prediction. If a rule is real, a true constraint of phi, then it will survive across measurement modalities within uncertainty. If the rule predicts a certain relationship between omega, k, and v, then that relationship should be recoverable from phi sentences reconstructed from acoustic, optical, thermal, mechanical, or any other valid probe of phi, provided those probes are capable of accessing the relevant omega, k, v regimes. The predicted pattern is modality transcendent, falsification of the rule's reality claim. If the law appears only in one sensor channel and disappears or is contradicted in others capable of testing the same omega kV relations, then it is an instrument artifact. The falsifying condition is failure to manifest in independent modalities. This doesn't mean the raw signal was fake. It means the interpretation of that signal as a phi pattern obeying a new rule G was incorrect. The signal was likely a product of the instrument's own physics, not the external phi. A clear historical example is the aforementioned N rays. Detected only by a specific visual observation method under specific laboratory lighting conditions, they vanished when tested with photographic plates or other detectors. They were an artifact of the observer's visual perception and expectation interacting with a particular experimental setup. Sensor model independence, trying a camera instead of the eye, falsified them immediately. Now, let's explore an Afghanistan-inspired analogy that ties together simulation, measurement, and reconstruction. Consider the task of assessing the snowpack in the Hindu Kush Mountains in early spring, critical for predicting irrigation water and flood risk. The phi pattern is the actual spatial distribution of snow-water equivalent, SWE. Modality 1, ground survey. Teams go to specific locations, dig snow pits, measure depth and density, a direct but sparse sample. Their instrument is a density gauge and a ruler. Their forward model is simple. SWE equals depth times density. Modality 2, satellite imagery. A satellite with optical and infrared sensors measures albedo and temperature. The forward model is complex, relating surface reflectance and temperature to snow depth and grain size, which correlate with SWE. Airborne LiDAR. An airplane flies over, firing laser pulses to measure the height of the snow surface compared to a summer bare earth model. The forward model converts height difference to snow volume, then to SWE using an assumed density. Each modality has different mixing of omega, k, and v. Ground surveys have excellent point accuracy, good k at a point, but terrible spatial coverage and are slow, poor omega for large areas. Satellites have excellent spatial coverage, good k over large scales, and good temporal repeat, omega, but poor vertical resolution and are confused by clouds. LiDAR has excellent spatial resolution and accuracy, but is expensive and has limited temporal sampling. A rule, G might be a predictive model. SWE decreases by 10% per week in April at elevations below 3,000 meters. For this rule to be licensed as a robust law of the local hydrology, it must be validated across these modalities. The forward models for each must be used to simulate what each should measure if the rule is true. Then, actual measurements are taken, reconstructed into SWE maps using each modality's pipeline, and the rule is checked. If the 10% per week trend is found consistently in the reconstructed phi sentences from ground surveys, satellite data, and LiDAR within the combined uncertainties, the rule earns a high confidence license. If it only appears in the satellite data, which might be confused by changing cloud cover or dust on snow, but ground surveys show no such trend, the rule is downgraded to a satellite artifact candidate. The firewall of good hydrology is this multi-instrument synthesis. Now, we must state the mandatory episode 11 axioms, now applied to the interface between reality and our senses. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. Sensor model independence is a direct test of independence. It is also a form of variation, varying the measurement interaction, and falsification, attempting to falsify with a different tool. Scope discipline is enforced by noting which omega k by v regimes each modality can access. And when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. Failure to achieve independence results in the rule being stuck at candidate or archived as sensor bound. The skill you gain from this part is modality triangulation. You learn to demand multi-pronged evidence for any extraordinary claim. You learn to be deeply suspicious of discoveries that live and die within the data stream of a single complex apparatus. You understand that reality must speak through multiple independent translators, and if they tell different stories, the problem is with the translators or our interpretation, not with the reality that changes its mind for each machine. This has profound implications for fields like parapsychology or searches for exotic physics. Claims of psychic phenomena or new forces often rely on one specific, subtle statistical effect in one type of experiment. They consistently fail the sensor model independence test. They cannot be detected by different, objective physical instruments designed to measure the supposed energy or information transfer. The firewall rightly keeps such claims in the candidate or artifact bin. Finally, let's summarize the epistemic function of this part. We have defined instrument-sensor model independence as the firewall requirement that a law must survive validation across multiple distinct measurement modalities. The protocol is simulate, measure, reconstruct, recover the same rule within uncertainty. Different sensors mix the triunity, omega, k, v, differently, but true constraints preserve the invariant relations. Energy tallies must agree across instruments. Disagreement indicates an artifact. The explicit prediction is survival of the rule across modalities, acoustic, optical, thermal, etc., within uncertainty. The explicit falsification condition is the disappearance of the rule when tested with independent sensor types. The license consequence is that the rule remains a candidate until independence is demonstrated or is archived as sensor-bound if independence is refuted. This strengthens the firewall by building a bridge between the abstract world of phi and the concrete world of engineered measurement. It ensures that our rules are not just consistent mathematical stories, but are forced to make testable, reproducible predictions for any valid listening post we point at the universe. It grounds science in a consensus of machines, not in the authority of any single machine. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There, you will find the scientific papers that this audio journey is built on. Carry the discipline of modality triangulation with you. It is your defense against technological illusion. In an age of ever more complex black box sensors, let this be your rule. One instrument, a curiosity. Two instruments, a hint. Three instruments, a fact. Now we bridge to the next and final layer of the firewall. We have ensured our rule is independent of specific instruments. But could our entire framework, our very choice of phi as the fundamental field, be a kind of instrument? Good. Now the next firewall. Does the rule survive not only different instruments, but different representations of phi itself? Salam and peace be upon you.